To session 18 of Complexity Explorer's MESA tutorial, Agent-Based Modeling in Python. Now that we've completed our agent behaviors and are managing the interactions through our model class and the step function, we're at the point where we can actually collect data and make sure our model's behaving in the way that we think it should. That being said, let's get started. So go ahead and open up your IDE or Google Colab instance and we can begin. So first, you want to make sure that you've linked your sugarmap.txt file to your instance. You do that either by mounting your drive or manually loading it. We have our helper function, which is currently get distance, but in this session, we're going to add a few more to help us analyze the data. And then we have our resources class of sugar and spice that grow 1 unit per time step, which we won't be interacting with. And then we have our trader class, which we completed in the last instance, where traders traverse the landscape and trade sugar or spice. Now, a critical point then is to make sure in both our calculate welfare, right, where we use the Cobb-Douglas function, or calculating the marginal rate of substitution, where we compare our spice and sugar in a ratio, right? That we've made sure that we've removed the math is close relative tolerance, so it defaults to its 9 decimal points. Right? This is important to help make sure that our agents are optimizing their behavior, so they're always improving their welfare by trading as much sugar and spice as possible based off how the Cobb-Douglas function and the MRS are calculated. Right? We also need to make sure that happens when our move function, right, when we try and find the optimal move locations based off welfare. Is anytime you're comparing two real numbers in computer programming, is you really want to make sure you understand exactly what you're comparing and what the impacts of the granularity that you use are. Because it's not going to be the trader function anymore. We're going to collapse that. Right? We will be working in the model class where we initiate the model. And in this initialization, we'll be adding another Mesa object class for data collection. Class also manages our step function where we use a staged activation with random activation for our traders. So we go through each of the sugar and spice functions, and then we go through our agents to move, eat, and possibly die, and then we go through our agents again to have them trade with each other. Now with the last one, we had a print statement after our agent.tradeWithNeighbors function that we can now delete. Model, make sure it's working, and delete your print statement. The next thing we're going to do is add an object, the data collector object from Mesa. So up here where we initiate our activation schedule, and we also initiate our Mesa grid class, we're now just going to initiate a data collector object. Like the grid and the schedule, we're just calling a Mesa class that will now be part of our model, just like with our trader or sugar or spice agents. So we'll call this self.dataCollector. And that will equal Mesa.dataCollector. That then gives us a data collector instance, right? And if we go up here, we can see from Mesa's GitHub page the data collector code. Again, this is all in Python, so you can see, you can look at the notes and see different options on how to collect data or process data using the Mesa data collector function. We now put in the variables that we want to collect. For the model, we want to collect 3 variables. First, the number of agents that are surviving at each time step, then the amount of trade volume that's occurring, and finally the price. So first, we'll get the number of agents that are still alive after each step. We'll call this one trader, and then we'll use a lambda function in order to get the data that we need. So Python primitive lambda for M, and this is short for model, and then that'll follow by colon, right? There'll be m dot schedule because we want to get the number of traders that we have at the bottom of any given time step. Right? So it'll be m dot schedule and then the random activation by type function get type count and then trader. As we could do it for sugar and spice, but those don't do anything except grow 1 unit. So we want to get our trader agent objects. So lambda m colon m.schedule get type count trader. And that will give us the number per time step of how many traders are left. Next will be trade volume. All right, again, we'll use a lambda function. So lambda m, which is just shorthand for model. And then we want to add together the length of all the trade partners for each of the agents. It'll be sum, open parentheses, len for length. And then we're going to do open parentheses again, A for agent dot trade partners. So this will collect the trade partners list for each agent object. All right, close parentheses, and then using list comprehension for A in schedule agents by type, and then trader in brackets. Right, so this iterates through the dictionary of traders and all their values, and each of those agent objects, it pulls out the list of trade partners, gets the length of those trade partners, and then sums them together for each step. I appreciate it's pretty condensed code that's doing a lot, but it's important, right? So m.schedules dot agents underscore by type open bracket trader close bracket dot values, right? So it's iterating through the dictionary of trader objects, and then pulling out the length of their trade partners and adding all those together. That's how we get the trade volume for each step. All right, so we're collecting model level variables for specific behaviors of the model. Okay, now we have one more to go, which is our price. And this is going to be a little bit more complicated because we're going to add two helper functions to it. So I'll name this one price with a capital P. And then we'll do another lambda function. Right, again, using M, which is calling the model object. And for this, we're going to calculate the mean kind of per growing artificial societies using the geometric mean, which we'll make a function for in a second. And because it's a list of prices that we want to get the geometric mean for, and each one of those is in their own list, we have to flatten that list, which we'll make also as another helper function. All right, so again, be geometric mean, open parentheses, flatten, open parentheses, and then list comprehension, a dot prices for A, and m dot schedules dot agents by type, open brackets, trader with a capital T, right, and then value. So again, this iterates through the dictionary of trader agents, takes that object, and then gets its price attribute from each of those agents. Okay? And then from that, we're going to do two functions. First, we're going to flatten it because it's a list of lists. And then from that flattened list, we're going to take the geometric mean. And so now we got our three collections that we do at each step across the whole model, where you get the type count of traders, the number of traders that are in each that are still alive, the volume of their trade by iterating through each of our agent models, and kind of their trade, and then finally we get the price. But we need to do some helper functions first. So first we'll do flatten, right? Work from the inside of our kind of condensed function out. Okay. And since this is, and we're going to put this in our helper functions outside of our model class, just where we put get distance for the last one. Okay, so flatten, and we'll take one parameter, which is a list of lists. Okay, so this is all the prices that the agents have collected, and each one of those, whether there's an empty list or not, right, will provide a list, right? And so it'd be item for sublist, list comprehension again, in lists of lists, right? For item in sublist. Okay, so what that does is it takes every item in each sublist and puts it into another list, which is what we're returning. So you gotta make sure there's brackets on beginning and the end. It's item for sublist and list of list for item in sublist. Right, and this just goes through each list inside that list of lists and extracts any price that was that was added during the model run and puts it into one flat list. And so we got to write some comments. So just again, kind of simplified comments, not formal comments. But this way you can understand your model a little bit better if you come back and look, or if somebody else does. And this will be a helper function for the model data collector. for trade price. As we're collecting three model level variables. And what this does is it collapses the agent prices from a list of lists into a single list so that we can then take the geometric mean in order to find out what the trade price was at each of those steps. So now I got to write our helper function for geometric mean. All right, so pass in our parameter, which is going to be the list of prices. And then we write our comments, uh, which is a list of prices turns into the geometric mean. More properly, find the geometric mean from a list of prices. So I got a comment. All right, should probably change our variable to actually describe what we're passing in. So that's list of prices. And this is actually coming from flatten. So that return function right there is just a list of prices. And then we can use NumPy, particularly imported, in order to calculate this. So we calculate the geometric mean is np for NumPy dot exp, open parentheses np log, right? And then pass in the list of prices dot mean. And so this is NumPy. It's very efficient calculator of arrays. All right, this will give us the geometric mean for the list of prices that we're passing in for each step. So that way, for each step, we could get the geometric mean for each price that was calculated. All right, so we pass the list of prices. We run this function to calculate the geometric mean, and now our helper function is working. So run that, no syntax errors. Then we run our model class, and we can see the three data points that we're collecting against our model, which is number of traders after each step, the trade volume of each step, and then the price, the geometric mean of the trade prices at each step. Right? And in the next lesson, we'll look at agent variables. Now, the one last thing to do to make sure your data collector is working is we need to put in the function to actually tell it to collect every time we run through one of the model step functions. So this is just one line of code, right? We've initiated our data collector at the top, where we same place we initiate our grid and our schedule. And now we want to make sure that we call the data collector during each step, so it collects these model level variables. And when we do our agent data collection, the next one, right, we'll put that inside the step function, so that way it collects more granular data for each agent. All right, so just put a quick comment here: collect model level data. Then we call our data collector instance, so self.dataCollector, and then we just use the function collect, which is part of the data collector class, and then self, and it will take care of the rest. So we run that, and then we're going to run our model. Okay, as now we actually want to collect a lot of data. Well, first we'll make sure it runs quickly, one step, and didn't get any errors. So now we can run 1,000 steps. And since our default keyword argument for step count is 1,000, we can run that. This should take, if you're using Google Colab, about 30 seconds. In the meantime, we can add another section called Analyze Data. So I added a text field called Analyze Data, and then once this is run, we can start to extract that data. We get a runtime warning, which is just telling us that during one step, no trade occurs. Sometimes these runtime warnings are really important, other times they're not, but it's important that you understand what they're saying as another way to verify your model's functioning the way they should. Okay, now the way we're going to extract the data is we're going to just create a quick function called results equals model dot data collector. So we're calling the model instance we created in the cell above, right? Dot data collector, and then we use the function .get underscore model underscore vars underscore data frame. So this is just a Mesa organic model that produces a pandas data frame, so it's easier to understand and analyze the results. So now we can just write results, run that cell, And sure enough, we get a table with what we were hoping for. So trader as our first one, number of traders still left alive. The volume, you can see there's a precipitous drop, right? And then the price which is a geometric mean of all the prices that occurred in that step. Okay, so we now have our data collection results. And so now I want to analyze them to see if we're getting results similar to that in growing artificial societies. Important thing to remember is, again, all of this code is available. If you want to see that particular function, you can just Control F, right, and get model vars, uh, data frames, look for that function, and you can see the actual function that you're calling. If you ever want to look at the code, if you're getting error messages that you don't understand, or you want to see how Mesa does it in case you need to make some adjustments to it. Right, so now that we got our results, we can start to plot things. As we're using a pandas data frame, pandas has some organic plotting functions that for this next one we're going to leverage. So we just do results dot plot, and then our y-axis is going to equal trader. And we're going to want to use the index and set that to true. So if you want to see this, you can look at the pandas documentation, and that's where we're getting our arguments from. But using this one-line function, we get a very kind of straightforward plot showing the number of agents that are living at any given time. Right? As always, I'll put some comments. So I'll plot number of agents per time step. All right, so again, results.plot y equals trader in parentheses with a capital T, and then use index equals true. Okay, now the next thing we want to plot is our price. Now we're going to try and plot this similar to how they plotted it in Growing Artificial Societies, which is a scatter plot, right, which is not part of kind of the pandas organic plotting function. Use the matplotlib normal functions to plot out the prices. So for this, we want to plot trade prices. We need to convert our column of prices just into a list that we can use for our y-axis. So y is going to equal list, open parentheses, results, and then price in brackets and quotes as it's calling that column. Right? And then x is just the range to 1,000. All right, so that'll give us just 0 1 to 1,000. There you just do plt.scatter. Remember, plt comes from how we imported matplotlib initially, right? So then it'll be x and y, and then size equals 1. This is the size of the dots, and we get an error. And that error showing us that path collection attribute has no property size. So sorry, it's actually s equals 1. And what that does is it changes the size of the dots because the default argument is just a little bit too big. All right, so go up here to plt.scatter. Again, plt is when we import a matplotlib, it's import, matplotlib.pyplot as plt, just kind of standard convention. And then we get the result. As you can see here, similar to the book, the density of prices around 1 gets more and more, and then the variance gets smaller and smaller as the code reaches equilibrium, right? So this is significant as this provides validation. The economic theory lets us know our model is working correctly, right? The number of agents, okay, that's consistent with growing artificial societies. Uh, uh, and then this next one, the trade volume, we'll see has is also similar but has some differences. But really, the one we care about is that our prices are converging to 1, right, which is consistent with economic theory. Right now, I want to plot our trade volume. This is where I'm going to show you an interesting dynamic. Right, so typically, right, we want a bar graph. Or typically might default to a bar graph because they're easy to do. So you just get plt.bar results.index, right? And then results trade volume. So it should be capital V. And this will tell us roughly how much trade is occurring, right? We get this huge drop off at the beginning. You can see there, or we have this huge spike, and then there's a pretty significant drop off. So, okay, well, that's kind of an outlier, right? You can easily get rid of that by just doing some cutting the list down, starting from 1, right? And we get this this dynamic of trade volume. Or we can see as agents die off, there's understandably less trade volume, right? Or is there. All right, so now if we look at 10, so let's say, well, so let's start with 10. Let's cut off all those two until we get the agent population stabilized. Right now we get this massive spike that we didn't have in the last one that goes up to 300. So similar to kind of math is close, what's happening here, right? Because the way matplotlib bar graphs work as it's creating container objects that, for lack of a better description, is just picking and choosing some of the things they're looking at. So if you actually want to get the amount of trade per time step and see what's happening, you have to use a slightly different function, right? So it'd be for I in range 1000, and then we got plt.v lines for vertical lines. I is your x-axis, 0 is your y minimum, and then results of your trade volume is your Y maximum. So this will plot a vertical line at each time step so you can see the trade volume. And then you put the I there for the index, right? And here it is, right? So this plots it out for us. We can see each one at the index, which will make sure that we get each step of trade volume. So the big lesson there is just, particularly doing visualizations, be careful that you understand exactly what that visualization is doing so you don't get false impressions about what's happening. All right, so that wraps up session 18. We do data collector, and then we made 3 visualizations where we kind of mirrored the critical result we wanted, which is trade prices converging to 1 over time, and the variance becoming less and less. Next lesson, we'll use data collector to collect agent level data so we can look at the trade networks of each agent. Next lesson will be batch run, where we do parameter sweeps and compare those results. Thanks for watching, and we'll see you in session 19.